Hello, today we're continuing with our series on A-level physics revision and we're continuing with our theme of electromagnetism. We are now going to look at electromagnetic induction. We've already considered a magnetic field and there are field lines associated with magnetic field which run from north to south. And we call the field strength B, that's the magnetic field. But if you take the field per unit area, so if we have, let's say, an area here, area A, and you have field going through it, then what's called the field strength per unit area, which is also called flux, which is given the sign phi, is equal to B times A. In other words, the flux is the strength of the magnetic field multiplied by the area through which it flows. In the case of a solenoid, which is several coils of wire, and let's say that the cross-sectional area of that coil is A, and that there are N turns in the wire, then the flux, or what we call flux linkage, which is given by capital Phi, is equal to BA, as before, multiplied by N, the number of turns, because essentially the flux, the magnetic field is going through the area not just once, but every time it comes to another coil it's going through that area again. So you've got N transitions, and that's why it's BAN. Now let's consider a wire in a magnetic field. And the magnetic field is going to be going into the paper, so we represent it as we did before with crosses in circles. That means the magnetic field is going downwards into the paper. And there's a piece of wire. Now we know that if we were to pass a current through that wire, then there would be a force on the wire, which is described by Fleming's left-hand rule. But suppose instead of passing a current through the wire, we were simply to move the wire downwards. Suppose we were physically to get hold of the wire and sharply move it downwards. Is it true that there would be a current flowing in the wire? After all, if a current flows in the wire in a magnetic field, it means that there will be a force that will push the wire down. If we do the pushing, will that induce a current? And the answer is yes, it does. It's called an induced current, and that is electromagnetic induction. Let's just repeat, there is a magnetic field and there's a wire. There is no current in the wire. And if you leave the wire stationary, there never will be. But if you take hold of the wire and physically move it downwards, you will cause a current to flow in the wire. Electromagnetic induction. But what direction does the current flow? We shall see in a moment, but first we just need to notice that the current will only flow while the wire is moving, and that means it's whilst it's cutting through the flux, not whilst it's sitting in the magnetic field. For example, suppose I had a coil of wire, this is a solenoid, and I connect it to an ordinary DC battery. And I have another coil of wire which is simply connected to an ammeter. There's no battery in this second circuit. Now there will be a constant magnetic field here, and the current on this will be zero. But if I were to take exactly the same arrangement, but this time I'm going to connect it to an alternating current mains, what you will see is on the ammeter that there will be an induced current that will flow round this circuit, and it also will be an alternating current, and that's called an induced current. It was Faraday who concluded that what's called induced EMF, which means electromotive force, was equal to the flux change divided by the time change. In other words, that could be represented as delta flux change divided by, or rather flux change, delta phi, divided by time change, which is delta t. Let's see if we can think of an experiment that will enable us to look at this. Here we have an electrical rod or thick wire. And what we're going to do is we're going to move it a distance x in this direction. The length of the wire is L. And there's a magnetic field of value B going into the paper. Again, we represent the magnetic field going into the paper with an X in a circle, rather like the arrow moving away from you. What is the flux that is going through this area? Well, the flux we know is equal to the magnetic field times the area. So the flux equals BA, where B is the magnetic field and A is the area that it's travelling through. But that's the same as Bx times L, because L times X is the area. So now we can say from this formula that the EMF is equal to the flux change, which is Bxl, divided by the time change, which is T. But X over T is simply the velocity at which this bar is pulled across this here. So X over T is simply the velocity. So we now have BLV, the magnetic field times the length of the wire times the velocity that it is moved across, is the value of the induced EMF. And now we come to a very important law, Lenz's law. Lenz said that wherever you have an induced EMF, then that EMF will always oppose the change that caused it. And so he said that the EMF is equal to minus d phi by dt. The minus sign shows that the EMF is opposing the change. And anything which opposes change is a resistance. So if we take a wire, which is in a magnetic field which is going into the paper, and we physically move that wire downwards, then a current will flow such as to oppose that force. In other words, a current will flow that will tend to cause the wire to go in the other direction, to oppose the force that's causing the current in the first place. Which means that if you apply the left-hand rule, you've got the magnetic field going into the paper, you've got the force going upwards because it's a resistive force, it's opposing the force that's going downwards. And that will mean that the current will flow in this direction. Think about it for a moment. If you had a wire with a current flowing in this direction, placed into a magnetic field which is going into the paper, that would make the wire go upwards. If instead you have a wire in a magnetic field and you physically move the wire downwards, a current flows in this direction such as to create a force in that direction in order to oppose the force that is causing the current in the first place, which is in this direction. Now, why does it work like that? The reason is because if it didn't, you'd have a kind of perpetual motion. Because what would happen is you would move, let's suppose it didn't work like that. Let's suppose that the current reinforced the force as opposed to opposing it. Then you would take the wire and you would jerk it downwards. A current would flow and the current would then cause the wire to move down even more. But that moving down even more would create an even greater current. And that greater current would cause it to move down even more, and that would cause an even greater current, and that would cause it to move down even more. You would get this perpetual feedback. And that's why Lenz's law says, no, it's the other way round. When you move the wire down, the current flows in such a way as to create a force in the opposite direction. Now we consider transformers and alternators. Let's suppose we have a solenoid, that's a coil of wire, attached to an alternating current. Remember, we need an alternating current because we need a current that's constantly changing, a voltage that's constantly changing, because only in changing flux do you get any induced current. And here's a second coil of wire which has got an ammeter connected to it. And when a current flows in this wire, it will induce, this will be an induced current, I induced, in this circuit. This is called the primary circuit, and this is called the secondary circuit. And of course the flux that is created in this circuit will be the flux that applies to this circuit. And what we find is that the voltage in the primary is the number of turns in the primary, that's the number of turns here, this is the number of turns in the secondary, times the change in flux, d phi by dt. The voltage in the secondary, which is an induced voltage, is the number of turns in the secondary times d phi by dt. It's the same d phi by dt because they both apply. And that gives you the formula that Vp divided by Vs is equal to Np divided by Ns. So if you've got different numbers of turns, you can get a different voltage. Vp is the voltage of the primary, Vs is the induced voltage of the secondary. Let's do a little example. Let's suppose that Vp is 230 volts. And let's suppose that the number of turns in the primary is 100 and that the number of turns in the secondary is 300. Put that into our formula and you will find that the voltage, the induced voltage for the secondary is 690 volts. So here's a means of stepping up or stepping down the voltage. Now, if this system were 100% efficient, then the power into this system would equal the power out of that system. And power, you remember, is the voltage times the current. So if it were 100% efficient, then the voltage of the primary multiplied by the current of the primary would equal the voltage of the secondary multiplied by the current of the secondary. And if that were the case, then Vp divided by Vs would equal Is divided by Ip. Now it isn't actually like that because you lose some power in the form of heat, but broadly that's right. And what that means is that for an induced voltage and induced current, if you step the voltage up, then the current goes down. On the other hand, if the voltage goes down, the current goes up. And this is precisely the principle that's used in the national grid. We start with a power station where alternating current is generated. That is then sent to a transformer which will push the voltage up to a very high voltage, hundreds of thousands of volts. And then that current is carried across the lines that go across the country until it gets to another transformer where the voltage is stepped back down again, and then that voltage is supplied to your home. Now, why do we step up and step down? Well, the reason is that the power loss in that cable is equal to I squared R. R is, of course, a fixed value for the resistance of the cable, which may be travelling over many miles. But you want as low a current as possible, because a low current will give you a low power loss. And as we've already seen, in order to get a low current, you need a high voltage. So if you transform this up to a very high voltage, it will be a very low current, and thus the power loss will be very low. But how do we create the alternating current in the power station in the first place? Well, this is just the opposite of, or using the same principle of, the electric motor that we devised earlier. We have a magnetic field, we have our wire, and we have our commutators here, such that as the wire goes round, first this wire touches this one, and then as it flips over it touches this one. In the electric motor's case, we actually drove a current through the cable in order to force it to go round. And then we had some kind of attachment here that would be the use of the motor. In a generator, what we do is we force this cable to go round by having some kind of steam that causes paddles to go round, and that will induce the current to flow in the generator. So it's just the same principle as the motor, except that with the motor we drove it with the current and caused it to turn, whereas in a generator we cause it to turn by using some kind of steam power, and as it turns there will be an induced current that flows, and when it flows out of here it can be sent on to be stepped up in order to be distributed to people's homes. Now we must remember that the flux is equal to the strength of the magnetic field times the area times the number of coils. Usually in a generator you have more than one coil, you might have several. The critical thing is, what is the area? If you've got your coil like this and the magnetic field is passing through, then clearly that's going to be the maximum flux. But as the coil twists, it will, here's the axis on which it's twisting, it will come to a point where it's flat and the magnetic field, as it were, is just skimming across it. It's not going through it at all. So the flux in this case will be maximum. The flux in this case will be zero because it's not going through any area. The coil is flat as far as the magnetic field is concerned, until it spins again and gets back to this position, in which case the flux will be maximum again. So what you've got is changing flux as this spins round, and that's a sine wave. The flux becomes equal to BAN, which is this term here, times the sine of 2 pi ft, where f is the frequency of rotation of this coil, and that will also be the frequency of the alternating current that that spinning coil will generate. And the final thing to explain is that the voltage will be what is called out of phase. The induced voltage and the flux linkage will be 90 degrees out of phase. What do I mean by that? Well, here's a graph. This is the flux linkage, which is a sine wave, and it varies between plus BAN, which is when this sine turn becomes 1, and minus BAN, which is when this sine term becomes minus 1. But the induced voltage is d phi, or actually it's minus d phi by dt. And if you take the derivative of that term, you get BAN, and then you have to take the 2 pi f outside, and now the sine changes to a cosine, 2 pi ft. So d phi, that's phi, with respect to t is BAN, bring the 2 pi f on the outside, change the sine to cosine, and that is d phi by dt. And in fact, the voltage then is minus that term. And that's a cosine term. And what that means is that when the flux linkage is at a maximum, the cosine term will be 0. And when the flux linkage is 0, the cosine term will be at a maximum. And so the induced voltage is going to look something like this. And as you can see, that is out of phase. This is the sine wave for the flux linkage. This is the sine wave for the induced voltage, and they do not marry up in terms of where the peaks fall. And what does that mean? It means that the induced EMF is at its greatest when cosine theta is 1. But when cosine of this angle here is 1, the sine will be 0. And that's when the coil is actually parallel to the magnetic field. So curiously, you get the maximum induced voltage when this is the situation, and you get the minimum induced voltage when it's this situation. The reason is that this gives you maximum flux because the magnetic field is passing right the way through the area. This gives you no flux at all because the magnetic field is going parallel to the coil. But because the induced voltage is 90 degrees out of phase, it means that this is the situation that gives you 0 voltage, and this is the situation that gives you maximum voltage. Hello, today we're continuing with our series on A-level physics revision, and we're continuing with our theme of electromagnetism. We are now going to look at electromagnetic induction. We've already considered a magnetic field, and there are field lines associated with magnetic field which run from north to south. And we call the field strength B, that's the magnetic field. In a magnetic field. And the magnetic field is going to be going into the paper, so we represent it as we did before with crosses in circles. That means the magnetic field is going downwards into the paper. And there's a piece of wire. Now we know that if we were to pass a current through that wire, then there would be a force on the wire, which is described by Fleming's left-hand rule, given by capital phi is equal to BA, as before, multiplied by N, the number of turns, because essentially the flux, the magnetic field is going through the area not just once, but every time it comes to another coil, it's going through that area again. So you've got N transitions, and that's why it's BAN. Now let's consider a wire, length of the magnetic field, multiplied by the area through which it flows. In the case of a solenoid, which is several coils of wire, and let's say that the cross-sectional area of that coil is A, and that there are N turns in the wire, then the flux, or what we call flux linkage, which is given. But if you take the field per unit area, so if we have, let's say, an area here, area A, and you have field going through it, then the what's called the field strength per unit area, which is also called flux, which is given the sign phi, is equal to B times A. In other words, the flux is the strength